Awesome. Hi. This video is going to be a mini lecture video specifically on the topic of Dijkstra and A-star algorithms. And this review will cater towards specifically the question 3 and 4 on tutor review session worksheet. So I hope you guys find this video helpful. And yeah, so let's dive right into it. So as we know, Dijkstra and A-star algorithms find or solve the shortest path problem. So what that means is that it helps us find shortest path on a certain graph, and specifically the shortest path between a starting vertex and some other vertices in a graph. And so specifically for Dijkstra, it finds what we call a shortest path tree. And so a shortest path tree, or SPT, is first of all a tree, which means that it is acyclic, and it also encompasses all of the shortest paths between whatever starting vertex you picked to every other single vertex in your graph. So in a sense, it is also a spanning tree, meaning that it spans across the entire graph and connects all the vertices in this given graph. And so because of that unique characteristic, we know that for a given SPT, it must have a number of v minus 1 edges, where v means or denotes the number of vertices in a graph. And so for all of the algorithms that we learned in this class, BFS specifically finds the SPT of an unweighted graph, meaning that all of the edges of this graph is unweighted. So here's like an example of that. And the SPT is highlighted in blue. And you can use BFS to kind of just double check if that's true. And for graphs that have weighted edges, you'll use Dijkstra and A-star. So how does Dijkstra work? When I think of this algorithm, I always have this mental image in my mind where I kind of imagine myself as an explorer. And I'm exploring this graph or like a map, I guess. And then every single vertex on this graph will be a certain destination that I want to visit. And the place I'm currently on, so kind of this position I'm currently on, will be my starting vertex. And my goal is to find a shortest path between this position I'm on to every other possible destination in this graph. And so that's basically what a Dijkstra algorithm does. And I like to think of it as I kind of came up on my own. So like, because I'm trying to find a shortest path between my starting vertex and every single other vertices in this graph, and given the fact I'm like a big brain CS student from Berkeley, I thought of this algorithm to help me do that. And I also love consonants, so I name it Dijkstra, which has like a million consonants in its name. But that's just like just to complete the mental image I always have. So with that in mind, what are the components of this algorithm or mechanism that we come up with to help us find the SPT of a graph? Well, the first component is that it definitely has a starting vertex, right? Because that will be our starting point. And then we also have this thing which is called a fringe or a priority queue. And you can kind of think of it as like this machine that when you feed in the vertices, you also tag them, like tag each vertex with a certain priority. And what this machine does is just basically sorts all of its vertices for you based on whatever like priority you tagged. And so in that sense, you can kind of like customize this priority, right? And so you have the control of determining what this priority would be. And so because in the Dijkstra case, we specifically want to find the shortest path. So naturally, we should probably make this priority of a certain vertex the distance between the starting vertex and this vertex that we're looking at. And so that's the fringe priority queue we're also using. And the last component is this dist2 and edge2 array, which is kind of just like the last bookkeeping tool that we're going to kind of use to help us reconstruct the shortest path tree. And specifically, the dist2 array keeps track of where did you arrive to that vertex. So let's say you have a row on this dist2 array that says vertex A, and then the value for that key is B. All that means is that the dist the edge to vertex A is vertex B. Yeah, so that's basically all what edge2 does. And the dis2 array just kind of keeps track of for each vertices in your graph that are not the root or starting vertex, what is the distance you have traveled to get to that vertex from the starting vertex. And so these are the components of Dijkstra. And on this right side here, I have this very high level overview of what the Dijkstra mechanism algorithm is. And so what you do is that you first initialize a priority queue with the starting vertex in it, and then you repeat the following 4 steps until you reach the stopping condition. And so the steps are, first you pop the node from the front of the priority queue. And remember that the order of the vertices are sorted automatically for you by the priority queue. And so when you do that, you also add the edge to this pop node into your storage path tree. And with this, obviously with the exception that if you popped the root node at the very, very beginning of your algorithm, you don't really do anything because that's kind of the starting point. But for every single pop node that comes afterwards, you'll do this. And step 3 and 4, you only do them if a better path is found. And what that means is that you're going to calculate a new priority based on the edge values of all of the unvisited children of this kernel you're looking at. This is a little confusing, but it will become a lot more clear if you walk through a specific example, which you will do later on in this video. And so what you're doing is kind of update this priority if this new priority calculated, or this new distance you calculated between the starting vertex and this current vertex you're looking at, is better than whatever metric you put it or you tagged on the vertex before. And so you only update it when it's better. And if you update the priority for this vertex, you also have to update the dis2 and edge2 values accordingly, just to make everything consistent, right? And so you keep doing this, and the step 5 is just restore the priority queue, because if you change the priority, right? But usually this is done automatically by the data structure itself. And so the stopping condition of this algorithm is that you have an empty priority queue. And that means that you can kind of consider all of the vertices in your graph, meaning that you have found a shortest path between the starting vertex and all of the rest of the vertices in your graph. I hope all of that makes sense. So what I'm going to do next is to go through a demo of the Dijkstra algorithm specifically on an undirected graph. And the example I'm going to use is just question 3A on a worksheet. Oh, and a note is that there's another walkthrough video on this problem specifically on 3A. And in that video, the TA didn't really go over the mechanical process of Dijkstra, and instead, he actually provided a pretty good test taking advice on this problem or this type of problem. So I will highly, highly suggest you guys to also watch that video. And this video will be more of a review on the little details of how Dijkstra works. Okay, so for this problem specifically, we want to find or determine what are all of the edges that will be in the SPT rooted in this vertex right here, so vertex L. And I always like to do a sanity check before I do any problems. And so for this problem specifically, the sanity check I ask myself is that how many edges would I have to write down to answer this problem, right? Because I know that I'm finding basically determining which edge in this graph right here will be in my SPT. And if I know I'm finding SPT using Dijkstra, then I know that based on the property we kind of discussed before, that it must have a v minus 1 number of edges, and where v is the number of vertices in your graph. And so for this graph specifically, it has 8 vertices, meaning that I probably have to write down 7 edges. And so you should always kind of do this just to make sure that you have a good intuition going into the problem. And so I know that I will have to write down 7 edges for the answers. Okay, so here's the demo, and let's just walk through it step by step. First of all, just some keep notes on the syntax I used in the diagram. All of this little blue notation on top of each vertex will be the priority for the current priority for this vertex. And this table right here keeps track of the dis2 and edge2 values for all of the vertices in my graph. And here's my priority queue. And down here, I keep track of the edges that are added into my SVT. And a note to that is I'm not only keeping track of which edge I added into my SVT, I'm also keeping track of the order of the edges are added. Okay. And so to initialize all the values for Dijkstra, because we don't know yet what is the distance, we don't know any information about what is the distance between the starting vertex and any of these vertices in the graph. And so I'm going to initialize all of them to infinity because that's as worse as it can get. And I'll update those values as I start exploring the graph myself. And so also a standard practice is just to initialize the dis2 and edge2 values for the root vertex like this. Okay, so because the starting vertex is the only vertex that has any non-infinity priority right now at the moment, I'm going to pop it, right? So L is going to be popped. Okay, and so in this diagram, I kind of checkmark the vertex that I have just popped or I have visited. And so what this means is just that this node has been visited. Because remember that for running Dijkstra on an undirected graph, it's important to keep track of which vertex is visited and which ones are not. So because I just popped L, I'm going to consider all of the unvisited children of L, which is U, T, and E. And notice that I have updated the priority for all of them. And the reason is that this new priority I calculated, which is 1, 9, and 4 respectively, they're all better than infinity, right? So I'm going to update that, and notice I kind of bolded the vertices in the diagram or in the table that have just been updated. And the vertex that has been bolded and has a blue color to it means that it is a vertex that just been popped. And so this is just make everything clear, crystal clear of what's going on. And lastly, in the priority queue, U, E, and T are also being updated for its respective priorities. And notice that it is also sorted automatically. And a last note is that on the diagram, I highlighted the edges brown to denote that they are the edges currently under consideration. So these edges are currently under consideration because they link the unvisited children to L. Okay, and lastly, no edges were added because the root vertex doesn't have an edge too. So it's still empty. I hope the first everything makes sense so far. Okay, so next I popped U, okay? And then because I popped U, I'm going to add the edge to U, which is from L, from this last update right here. Notice what I had for the edge to value. So I'm going to add this edge into the SPT. And I also denoted that down here. And because I popped U, that means I visited the vertex. So I'm also going to place a check mark there. And then next step is to check for each unvisited vertex of U if I have to update anything. And it turns out I did update. And so for the priority for specifically, if I'm looking at I first, I calculated the new priority to be 7. Why is that? Well, the path of travel to reach to I, it was from L to U to I, right? And this distance is 7. And 7 is better than infinity. And so I'm going to update that. And similarly for T, I arrived to T from L to U to T. And this path has a total distance of 3. And 3 is also better than infinity. So I also updated that. And because I updated them in the dis2 and the edge2 and also the priority, I kind of bolded all of them. And notice that the priority queue is also kind of resorted by itself. So this is the next step that we have. Following that, I popped T. And so because I popped T, I'm going to add the edge to T or UT into my SPT. So all the edges that are currently in the SPT are highlighted yellow. And the next step is to check all of the unvisited vertices or children of T. And notice that because U and L are already visited, which I have like a check mark next to it, I'm not going to check those edges. And notice that none of them are highlighted brown. And so these 4 are the only 4 edges I'm going to consider because they link to an unvisited children or child. And so I do the standard procedure of checking, okay, I calculate my new priority, and for I is 1 to 2 to 7, which is 10. And because 10 is worse than what I already had there, which is 7, I'm not going to update I. So notice how in this diagram, in this table, I is not bolded because it remained the same from the last update. And then for A, this new priority I calculated was 3 plus 3, which is 6, and 6 was better than infinity, so I updated that. And then for S, I also calculated the new priority to be 8, and A is better than infinity, so I also updated the priority for S and also the corresponding Des2H2 values. And then lastly for E. Well, for E, the new priority I calculated was 3 plus 6, which is 9, and 9 is worse than 4, so I'm not going to update that. And so E also remained the same. And that's all the updates I did for this iteration. Okay, moving on. Here, which one did we just pop? Okay, so based on priority here, we just pop E, and so E is highlighted blue. And so if you're looking at E, the only after adding the LE edge into our shortest path tree, the only unvisited child of E is S. And the new priority calculated from that is 9, and 9 is worse than 8. And so we're not going to update anything for S. And so nothing got updated in this iteration. Okay, next we popped A. And so notice how A is highlighted blue. After popping A, we add the TA edge into the SPT because that was the edge 2 value for A. And then for every single unvisited children of A, which are highlighted with brown edges here, I checked if I need to update anything. And turns out I updated the values for both of them. And so the reason for that is from A to I, this is a shorter path that we just found, which has a total distance of 6, and 6 was better than what we had before, which is 7. And so I updated the value for I updated this to H2 value as well. And then for M, this new priority calculated was 9, and 9 was better than infinity. And so I updated it for M as well. Awesome, we're almost done. So the next one, we popped I, and the only edge that we had to consider was from I to M after adding this edge into our SPT. And so this new priority we calculated is 10, and 10 is worse than 9, so we don't update, and nothing got updated this iteration. And next iteration is popping S, and the same observation and same conclusion was reached, nothing got updated. And lastly, we popped M. And so after we popped M, we visited all of the vertices. Also, nothing got updated because it's kind of the last one. And then we're done because the priority queue is empty now. And so what you should notice is that at the end, we have the edges. The edges are added into the SPT are UL, UT, LE, AT, AI, ST, and AM, which are all highlighted yellow here. So I hope that was a very, very clear walkthrough and demo of running Dijkstra algorithm and an undirected graph. And if you want to learn more about how to kind of solve these problems more like fast and more efficiently, given the time constraint during an exam, like I said before, I will direct you to the walkthrough video of this problem that are linked in the solution. And I think Soham provided a very nice technique to do that. And I will divide this video into halves. So the second half of this video will review the A-star algorithm and also its mechanism.